Now let's get back to the question of why or how we can model this thing with the electron not dissipating all its energy in the form of high energy electromagnetic waves or high frequency electromagnetic waves. This doesn't happen, we can say, because angular momentum is quantized. Okay, what's that mean? Angular momentum. The angular momentum of the electron rotating around the proton is simply the product of its angular velocity and its moment of inertia. Now the angular velocity is just v over r, the moment of inertia is mr squared, so this just really comes out mvr, and that is quantized in the sense that it's an integer multiple. Here n represents an integer equal to 1, 2, 3, 4. Actually, it's a whole number, or a counting number multiple. These are the counting numbers. They have to be non-zero and positive. So it's a counting number multiple of h over 2 pi. Now what's this h? That's Planck's constant, approximately 6.64 times 10 to the negative 34th joule seconds. Okay? And joules times seconds are units of angular momentum. So when we multiply this by some whole number or some counting number n divided by 2 pi, we get a possible angular momentum for an electron. Electron can't have any other angular momentum. That's what we mean when we say it's quantized. It's going to be 1 times h over 2 pi, or 2 times h over 2 pi, or 3 times h over 2 pi. Never 1 1/3 times h over 2 pi. Never any other multiple. Always 1, 2, 3, 4, 5 counting number multiples of h over 2 pi. This means that the electron can't continuously spiral down in its orbit. It means that the electron can therefore not continuously dissipate energy. And as a result, our model tells us that the electron can orbit without losing energy to electromagnetic radiation. As a matter of fact, it can't lose energy to any continuous electromagnetic radiation, although it can lose energy to discrete packets, as we'll see. Discrete packets of electromagnetic radiation. Now, if we take this condition, the angular momentum quantization, mvr equals nh over 2 pi, and we abbreviate this h over 2 pi. It's a pain to keep writing h over 2 pi. We write that as h bar. We put this little bar through the h, and we read that as h bar, and this symbolizes h over 2 pi. So that we can simply write mvr equals nh bar. Now recalling that if we set the centripetal force equal to the Coulomb force, we get V equals this proportionality constant times 1 over the square root of R, approximately equal to this when we evaluated the proportionality constant. We have an equation involving V and R and a bunch of constants, and up here we have an equation involving V and R and a bunch of constants. This mass here is the mass of the electron, so this should have been written ME, but we kind of lost that. But the point is, now we have two simultaneous equations in V and R. V and R are the only variables in this equation. They're the only variables in this equation. We can therefore solve these equations simultaneously to get specific values for V and R. And when we do that, as we do down here, we simply substitute, well, we set okay, NH bar stands for MVR, and we just do MVR with this expression for V. So here's M, here's V from this expression, here's R, and we set that equal to NH bar. There are lots of ways we could solve this simultaneously. That's just the way that we chose to do it this time. In any case, we see that MVR from this expression for V equals MVR, which is NH bar, from this expression. We solve this for R, and we see that R is going to end up being equal to the square of n, our integer, or our counting number, times h bar squared over MEKQE squared. And the algebra here is simple. I just got 3 dots down here. You should be able to solve this equation for R. And when you do, you'll get a solution that you see can be put into this form. I'm not going to go through the details of that algebra. Distracting. That would distract everybody from the purpose here. So we just do the algebra, and this is what we get. Here are our allowed values of R. R is n squared h bar squared over mk qe squared. Now, when we evaluate the term in brackets, or the factor in brackets here, we get 0.529 angstroms. So R is going to be just n squared times 0.529 angstroms. V, remember now V was this proportionality constant times 1 over the square root of R. What's that equal? Well, if we substitute this for R, now we're going to get something like this. And we get V is approximately equal to the reciprocal of our n times 2 times 10 to the 6th meters per second. That's just a rough approximation. It'll actually, I think, be times 1.6 times 10 to the 6th meters per second. But we're just doing a rough approximation here. Okay, so by solving the equation simultaneously, we get an equation for R. We can substitute that into the expression for V and get an equation for V. And we can evaluate these numbers that I've approximated here to as many decimal places as is appropriate given our knowledge of H, M, E, K, and QE. To whatever significant figures we know these quantities, we calculate V in this form to that many significant figures.